Section 4.6, Applications and Models of Exponential Growth and Decay, Part 2 of the notes. Example 3 has to do with population. According to the U.S. Census Bureau, the world population reached 6 billion people during 1999 and was growing exponentially. By the end of 2010, the population had grown to 6.947 billion. The projected world population, T years after 2010, is given by this function. Part A, based on this model, what will the world population be in 2020? So first of all, we need to figure out what to plug in for our years. We're not going to plug 2020 in. T equals 0 was at 2010, so we're going to use T equals 10 since 2020 is 10 years later. So we take the formula that we were given on the last slide, and we're going to plug 10 in for T and evaluate. We get approximately 7.484. So our answer is the population will be 7.484 billion at the end of 2020. Just a quick side note, since it's 2021 when I'm making this video, hello to people in the future, I just went ahead and Googled it to see what the population was at the end of 2020. And according to Google, it says it was 7.8 billion people. So our estimation was a little off, but still trending in the right direction. Part B, in what year will the world population reach 9 billion? So again, we're going to use this formula. And this time we're going to take 9 billion and plug it in for our y, or in this case, f of t. Start by dividing over the 6.947. And then since we have a base e on the right side, we're going to take natural log of both sides so that the natural log and the base e will cancel out on the right. Now we can divide both sides by 0.00745. And we get an answer of t is approximately 34.8. Remember, t is years. It's not year 34.8. It's actually going to be the years after 2010. So this would be the year, roughly, 2044, when the world population will reach 9 billion people. Example 4, determining exponential function to model radioactive decay. Suppose 600 grams of a radioactive substance are present initially, and 3 years later only 300 grams remain. Determine the exponential equation that models this decay. So we're going to start with our exponential growth or decay equation here. And we initially started with 600 grams, so we're going to plug that in for y naught. Next, we know that 3 years later, so when t is 3, there's only 300 grams remaining, so we're plugging that in for y and t. That way we can solve for k. Start by dividing both sides by 600. And then we're going to take natural log of both sides. On the right side, natural log and e will cancel out. And then we can divide by 3. That gives us an approximate k value of negative 0.231. It makes sense that k is negative since we have a decay situation going on here. So we get our exponential model of y equals 600 e to the negative 0.231 t. Part B, how much of the substance will be present after 6 years. So to find that amount present after 6 years, we're going to let t equal 6. And we're just going to plug that into the equation that we just found. Put that in your calculator, evaluate it, and we get approximately 150. So after 6 years, there's 150 grams of the substance remaining. Example 5, solving a carbon dating problem. Carbon-14, also known as radiocarbon, is a radioactive form of carbon that is found in all living plants and animals. After a plant or animal dies, the radiocarbon disintegrates. Scientists can determine the age of the remains by comparing the amount of radiocarbon with the amount present in living plants and animals. This technique is called carbon dating. The amount of radiocarbon present after 10 years is given by this equation, where Y0 is the amount present in living plants and animals. Example 5, Part A, find the half-life of carbon-14. So first of all, we're going to think about if Y0 is the amount of radiocarbon present in a living thing, then half of Y0 is half of its initial amount. Thus, we substitute and solve the given equation for T. So instead of Y, we're going to plug in 1/2 Y0. That's just saying half of what we started with, half of our initial amount. Next, we can divide both sides by Y0 and then take the natural log of both sides. Natural log and the base e cancel out. And then we can just divide by the decimal on the right side with t. In the end, we get t equals 5,700. So the half-life is about 5,700 years. Part B, charcoal from an ancient fire pit on Java contained 1/4 the carbon-14 of a living sample of the same size. Estimate the age of the charcoal. So again, we're going to plug in 1/4 of Y0, so 1/4 of the initial amount. We're going to plug that in for Y, because we want to know when we've got 1/4 of the initial amount left. Next, we will divide both sides by Y0. And then take the natural log of both sides. Natural log and base e cancel out. We divide by our decimal, and we get t to be approximately 11,400. So the charcoal that they found on Java is about 11,400 years old.